Okay, in this video clip we're going to be examining units, especially introductory units, the basic SI units that we use in physics. And we're also going to be starting to look at the prefixes that we use with units to deal with enable us to deal with very large or very small numbers. Okay, so let's start with the basic thing. We're using, in most countries in the world, we use the SI system, the System International, and which it's very similar to the metric system and has a lot of the same basic measurements. Okay, so the basic SI units. Okay, so pretty much officially everything we measure in the universe can be measured with 7 different quantities. Some of these we will be using in the next lessons, a couple we won't, but let's just put these down and then we can deal with the appropriate one. Okay, so the first one is displacement. Also sometimes called distance. They're not quite the same thing, but at the moment let's just go with distance, displacement. So displacement is distance from here to here, or shift something that was here is now here, so it's being displaced. The measure of that is going to be meters, the length. So hopefully you know what a meter is. Okay, so that's the basic one. Another one is going to be time. Time is probably the most accurate thing that we can measure. So time, we actually nowadays tried to make distance a function of time. So we tried to make distance somehow related to time because we can measure time so well. So the question is, what's the base unit of time? The base unit of time is the second. Yes. This goes back to historical reasons, but it works fine. What else do we have? Distance, time, mass. Remember, on Earth, mass and weight are virtually the same, but there is a difference. Mass is an intrinsic property of something, weight is a force. So there is a difference between mass and weight. Let's deal with mass. The basic, for some reason, which I've been unable to determine, the base unit is a kilogram. So it gets a kg. What else do we have? We have temperature. Okay. And temperature is measured in Kelvin. Now, a Kelvin, the difference between Kelvin and Celsius is where you start measuring from, where you measure 0 from. 1 degree Kelvin, change of temperature 1 degree Kelvin is the same as 1 degree Celsius. But 0 degrees Celsius is defined as where water freezes, or it used to be defined as where water freezes, then it became the triple point there. Yep. So 0 degrees Celsius. 0 degrees Kelvin is absolute 0, so that's minus 273 Celsius. So with Kelvin, the only difference is where do we start measuring from? Don't get too hung up on that. As required, I will explain further. So Kelvin, because Kelvin was a real guy, Lord Kelvin, he gets a capital K. As a rule with units, if the person was a real person, then they get a capital letter. So Newton's, because Newton was a real guy, capital N. Curie's, because Madame Curie was a real person, her unit gets a capital CU. Okay, displacement, time, mass, temperature, amount of substance. This one's used a lot by chemists. It is used by physicists, but not in this. I'm not going to be teaching this in the course, but it's just general. It's measured in moles. Mole wasn't a real person, maybe a small animal, but it wasn't a real person. And what else do we do? Current, electrical current. It's measured in amperes. we will be dealing with that in the electricity section. Because ampere was a real person, gets a capital A. And the last one is luminous intensity. Which is measured in candela. Okay. This last one is a bogus unit. These, displacement, time, mass, temperature, amount of substance, current, okay, they're all base units. This one can be made up of these units. And what's worse, this one is weighted for the human eye. What's the human eye got to do with the universe? So, while that's an official basic SI unit, it's bogus. So basically everything we know in science, especially in physics, can be described with these 6 quantities. Can be described with displacement, time, mass, temperature, amount of substance, and current. I don't know about you, but I think that's bloody amazing actually, that we can basically reduce pretty much everything in the universe down to 6 things. Okay, so then we have derived units. We will use derived units as required. What I mean by derived units is these are units made up of the base units. So, derived units, like velocity, is measured in meters per second. You can see the meters is there, seconds there. Acceleration, meters per second squared. What else? Voltage, joules per coulomb. 1 joule, well, joules. Joule is kgs meters squared per second squared. As you can see, joule has got mass. It's got meters. It's got seconds. So volts is going to have pretty much all of these. Okay, so derived units are made up of those 6 units. We'll have quantities of those 6 units in it. Okay, let's just shift on now to the system of prefixes. Because in physics particularly, some of the numbers we deal with are very, very large and can be very, very small. Like the biggest number I know of is 10 to the 10 to the 67 years. According to Freeman Dyson, this is the heat death of the universe. If we try and write that down on a sheet of paper, there isn't enough ink in the universe there isn't enough ink and paper in the universe to do that. So we need a different way of writing this. Smallest numbers, we get down to like 10 to negative 18 seconds. This is like half-life of very unstable things like hydrogen 8. So, instead of writing 0.0000000000000001 seconds, there must be an easier way of doing this. I mean, it just gets ridiculous if you're going to write that all the time. And there is an easier way. What we do is we have a system of prefixes. We have our basic unit like an M or an S or a kg, and then we'll put a letter in front of that, and that will tell us, that will modify it, either make the unit bigger or smaller. So let's try it. Let's just get rid of all of this. Okay, so if we have a base unit, let's try our seconds. Well, it doesn't matter, this works pretty much for all units. So if we have a base unit, seconds, 1. Okay? So if we're talking bigger numbers, if we have a kilosecond, kilo means times 1,000. So 1 kilosecond would equal 1,000 seconds. 2 kiloseconds will equal 2,000. When I see kilo, or that K, it means to get to this unit, I go times 1,000, or times 10 to the 3. So, another one, the next one up, surprisingly, well, it's not actually surprising, this goes up the same way computer memory does, because computer memory, the way we label computer memory is based on the system. So if we're talking bytes, you have 1 byte, you have kilobytes, the next one up would be megabytes. Same here, we'd have megaseconds. Mega means mega times 1,000,000. So if I was going to convert from megaseconds, okay, you have to make sure that's a big capital. If I'm going to convert from megaseconds to seconds, I have to multiply by 1,000. If I'm going the other way, I'll divide by 1,000. But, so, 1 megasecond has 1,000,000 seconds in it. Okay, so if you were talking computers, what's the next one above mega? Gave it away there, didn't I? Giga. So giga means times an American or a French billion times 10 to the 9. So 1 gigasecond would have 1,000 million seconds. Next, if you're talking computers, the one above giga is tera. Tera times, sorry, this could take a while, million seconds, or a trillion. Okay, so that's getting bigger, and above tera goes peta and so on. We go up to about 10 to the 21. What happens if we're getting smaller? That's the next question. So, is there a unit smaller than 1 second? And the answer is yes, there is a millisecond. Notice this is a small m. That's capital, this is a small m. Milli means times 0.001, or 10 to the negative 3. So there is 1,000 milliseconds in 1 second. In fact, that's what milli means. Milli comes from the Roman word for 1,000. In fact, the word mile originally meant 1,000 because there were 1,000 paces in a mile. And before you think the Romans had very, very big steps, it's because 1 Roman pace is 2 steps. So left, right is 1 pace for the Romans. So milli means there's 1,000 per second. So, next question is, micro. Is there something smaller? Yes, microseconds. Notice this is the Greek letter mu. Or mu. This is an M because we're talking micro. We've already used little m here and capital M here, so we use a Greek little m. Okay, so that's times 0.000001, or times 10 to the negative 6. And is there something under that? And the answer is yes. Nano, like you've heard of nanotechnology, hopefully. So nanoseconds, nano times 0.000000001, or times 10 to the negative 9. And is there something below that? Of course there is. There's pico. 0.0000000000001, or times 10 to the negative 12. Question is, would you actually use a prefix that small? And yes, you would. This would be, you get capacitors and things down in picofarads. We talk about nanoseconds in computing now. Nanotechnology means things nanometers in size. So when you're talking power, you can be talking terawatts, terajoules. So yes, we can use all of these in ordinary physics without getting too worried about it. Okay, so converting. So say I'm converting one unit to other ones, like milliseconds, to microseconds. So if I have a number, i.e. 236 milliseconds equals how many microseconds? Yep. What I'd do is I'd shift the decimal point. I got milliseconds times 10 to the negative 3 times negative 6. Because it's negative, because we're going this way, shift decimal point right. Okay, so if we're going this way, down, we're going to shift the decimal point to the right. I'm going from negative 3 to negative 6, so the difference there is 3 decimal places. And this says we're going to shift it to the right, so we're going to go 1, 2, 3, so that's going to equal 236 microseconds. Okay, let's try this again. Okay, I want to convert, I don't know, 6,543 nanoseconds to microseconds. This time, because we're going up, shift the decimal point left. Yep. So, what's the difference? It's negative to 3 to negative 9 to negative 6. That means we're shifting it 3 places. It also says, because we're going up the graph, we're going to shift it to the left. So the decimal point starts there. So it goes 1, 2, 3. So that's equal to 6.543 microseconds. Okay, so what I'm trying to say here is when we're converting, if we're going down the table, if we're starting from a big number, big unit, and going to a small unit, we shift the decimal point right. If we're starting from a small unit and going to a bigger unit, we shift the decimal point left. And this tells us it's the difference in number of decimal places, it's the difference between these indices that tells us how many decimal points. So if I'm going from here to here, the difference is going to be negative 12 by 6. It's going to be 18 places we're going to shift it. If I'm going from here to here, that would be 3 places. Okay, so what we have to do here, when we're converting, we have to figure out 2 things. We have to figure out how many decimal places we're going to shift it. So step 1, how many decimal places we're going to shift it. We look at that by looking at these indices. Step 2 is which direction are we going to shift the decimal point. And that is determined by whether we're going up or down the graph. Whether we go going up, we go left. If we're going right, we go down. So if the unit's getting bigger, we shift the decimal point left. If the big unit's getting smaller, we shift it right. Okay, that's probably enough on units by now. You're probably sick and tired of hearing about units. So I'll catch you in the next section where we're going to start dealing with some kinematics, hopefully. We'll start dealing with displacement time graphs. Till then, yep, happy physicking.